All right, I think we're recording there. We're live on Zoom. Good morning, everybody. Hope you had a delightful Halloween and were safe and all of that. My children, the younger ones, spent most of Saturday morning telling me how I didn't understand how much I was ruining their lives by not letting them go trick-or-treating because of COVID. And that everybody else was trick-or-treating. Turns out it was a very light night for trick-or-treating. We didn't see that many people out. So we tried to point out that we are not the jerks that they think we are. But our argument was not persuasive. So, but anyway, it ended up being fine. And if you haven't voted yet, make sure you go vote. I make no statement as to political preference. The church, of course, is politically neutral, but you should exercise your right to vote. And after tomorrow, well, it may not actually be done tomorrow, so stay tuned. It's going to be fun. That's right. I was actually just returned from my mission in 2000 when the Bush-Gore debacle happened, and we didn't know for a couple of weeks what was going to happen. All right. So kinetics, we've sort of talked through potential energy surfaces and transition state theory. We've talked about I-ring plots and how to get enthalpy and entropy of activation out of stuff. I thought since there are a number of reactions that are common that are tabulated in this image that I'd show it to you. This gives you a sense for the scale of entropy, activation entropy changes in various chemical reactions. Your text points out that it's not really fair to compare activation entropies for reactions that have different molecularities. Of course, a bimolecular reaction is going to have a different activation entropy than one that only requires one molecule. And you have to also factor in the various solvent effects. One thing I don't like is that they're showing you these EU entropy units, which mean, I think, calories per mole per Kelvin. In my lab, when we want to talk about entropy, we just convert it into minus T delta S so that you can look at the impact of entropy on free energy, and then you can talk in kcals per mole and people understand you better. But in any case, just looking at the magnitude here, for the reaction where rate determining step of acid catalyzed hydrolysis of ethyl acetate, rate determining step is attack of water on the carbonyl carbon to give a tetrahedral intermediate. The transition state, accordingly, because it involves two things coming together, has a fairly negative, that is, unfavorable activation entropy. In contrast, the hydrolysis of this methyl glycoside, the rate determining step is the kicking off of the protonated methoxy group by the ring oxygen, and to give you the oxonium ion, and that is taking one thing and turning it into two, and the transition state resembles presumably the leaving of this group, and so that activation entropy is actually favorable. Similarly, in an SN2 reaction, you have two things coming together. It makes sense that that activation entropy should be unfavorable. SN1 reaction, the leaving group is leaving, two things out of one, you see activation entropy to be favorable. Go ahead.
So we often talk about, like, obviously activation entropy, and we draw the little thing.
Yeah.
Transition state. Is this just, like, we wouldn't graph something like this, right?
You could. Yeah, but it would be fine. I mean, you could draw, I don't know, entropy over the course of a reaction, and depending on the reaction, you might find that you would see. I don't know what exactly you would see. But remember, you don't, because entropy affects delta G unfavorably, you have to interpret maxima and minima differently. That's why if you were going to plot this to communicate without confusion to your readers, if you do minus T delta S, then you can plot it in a way that affects free energy. So yeah, we're not, your book has given no reaction coordinate energy diagrams with entropy. Typically, these values that you would get for a reaction would be constants that you would get by plotting doing the I-ring plot, which we talked about last time, and I don't remember. This is rate constant, and then you've got a whole bunch of other constants in the expression. Boltzmann's constant, the mysterious kappa, which we have to draw kind of funny, and then I'm getting that wrong. The activation enthalpy is the slope of the plot of the log of the rate constant versus 1 over T, and then the activation entropy is the intercept. And so these numbers presumably are the constants they got from doing the I-ring analysis and you get that by varying temperature and seeing what the rate does. Okay? But this is all for a process that you sort of already know about. And these, at least the derivations that we're looking at, seem to have been for simple one thing converts into another through a single transition state. Of course, we know in organic chemistry those reactions can get quite a bit more complicated than that. So we're going to spend a little bit of time talking about ways that organic chemists simplify our understanding of kinetics, and then we'll start talking about some of the possible rate laws. We're going to do that not so you can memorize them, but so you can know at some point in your future, if you need to do a kinetic experiment, you know where to go to find the appropriate rate law and what hypotheses to test. All right, so before we do that, let's talk about some basic assumptions, postulates, things that make kinetics a little bit easier for organic chemists. The Hammond postulate. So that's something that you guys learned about in sophomore organics. So why don't somebody tell me what the Hammond postulate is? Okay, Dakota, go ahead.
If the product and reactants are at different energies, the transition state has to resemble whichever one is higher.
Okay, if the product and the reactants are at different energies, the transition state has to resemble whichever one is higher. Okay, that is a correct application of the Hammond postulate, though we want to add some quid pro quos and caveats and whatever to show you, to give you a sense for what the limitations of this are. So the first limitation is that the Hammond postulate is not only about transition states, it's about any point on a reaction coordinate energy diagram. Remember that the reaction coordinate represents geometry of the molecule. So if you have two adjacent states on an energy diagram or a potential energy surface, and they are similar in energy, they have to be similar in structure. And this is why, you know, the real important point here is adjacent states, because of course for a multi-step reaction, what the heck am I doing? For a multi-step reaction, you could say, oh, well, this transition state 2 resembles the free energy of the starting materials more than the products, and therefore nothing. They're far apart in reaction coordinates, so you can make no connection between the two of them structurally. But if you have two positions that are close, two adjacent states that are close on the potential energy surface, if they're similar in energy, they have to be similar in structure. Go ahead.
So does adjacent here just mean close, or does it mean something more specific?
Immediately adjacent. I think we're talking about intermediates / transition states and products, right? So I guess what I mean by that is in a multi-step reaction, various points on the free energy surface, A is adjacent to B. B is adjacent to both A and C. In this case, probably B is, let's make it a little bit easier to work with. I still didn't do what I wanted to do. Let's see. Partial, erase. All right. So the Hammond postulate would tell us here, B is adjacent to positions A, intermediates or starting materials, minima in the potential energy surface A and C. It's closer in energy to C, so it has to resemble C more. Okay? B, so let's just formulate the analysis. B is adjacent to A and C, but closer in energy to C, therefore must be closer in structure to C. And a classic example of this kind of reasoning is one you've seen before. Why are there pictures of Jack's friends on my iPad? Oh, Jack used the iPad yesterday for his young men's, and apparently that involved exchanging of pictures through Zoom, so I apologize for that. Classic example of using the Hammond postulate to connect the structure of a transition state to the structure of an intermediate is this first step in the SN1 reaction, where you have carbocation stability here, methyl, ethyl, propyl, T-butyl. T-butyl is the most stable intermediate. The transition state leading from alkyl halide or whatever leaving group to the carbocation, that transition state is in each of these cases closer in energy to the carbocation. Therefore, the transition state that leads to the more stable carbocation is the one that happens faster. All right. Some people try to some people try to simplify the Hammond postulate by saying, okay, if a step is endothermic, uphill in energy, the transition state, it must be the same, it resemble the intermediate. That works, but it's not the original sort of formulation. It's all about proximity of two different states in energy on the potential energy surface. Okay. You'll hear people talk about early versus late transition states, and you may wonder, okay, what's going on there? In this image, your text is trying to show you that the two-dimensional reaction coordinate energy diagram that we have is really just a slice of the potential energy surface. In this case, the transition state is closer in energy to the starting materials than the products. Because of that, it's also closer in reaction coordinate, because these things are tied together, right? Energy and geometry. And so the transition state appears earlier on the reaction coordinate diagram because it's closer in energy to the starting materials. In this case, the transition state is quite different from both starting material and product, so it appears somewhere in between the two. And then this would be called a late transition state because you're going uphill in energy and the transition state is closer in energy and in reaction coordinate to the intermediate, and therefore resembles that high energy intermediate. Okay, so we've used that before to rationalize SN1 reaction rates as a function of alkyl halide structure. Any other questions about the Hammond postulate? Honestly, I wouldn't make it any more difficult. If I were you, I wouldn't make it any more difficult in my mind other than, okay, if two adjacent states are close on the potential energy surface in energy, they also have to be close in geometry. Okay. Another rule of thumb that you will hear in organic chemistry, and this one has been somewhat controversial, is the reactivity versus selectivity principle. And this one is useful sometimes, but there are notable exceptions to it, so you have to view it with caution. The idea is that less stable or more reactive starting materials or intermediates are less selective. If there are multiple options in terms of regiochemistry, the idea is that more reactive reagents will be less selective. Years ago, Dr. Savage explained this to our class by saying that imagine you are trying to use willpower to improve your eating. If you are very hungry, that is highly reactive. But then this falls apart because when I'm highly reactive, I don't... Oh, right, that works. When you are very hungry, that is highly reactive, you are less likely to make good choices. You'll open the fridge and eat whatever horrible thing that's bad for you. For me, it's carbs. I'll start munching on crackers of various kinds, and before I know it, I'm 700 calories in, and this is why I look the way I do, and this has become kind of uncomfortable, so we'll just move on. But on the other hand, if you're not as hungry, you tend to make better choices. An example of this chemically that tends to work out is radical halogenation of hydrocarbons. So, for example, in this particular hydrocarbon, 1-methylpropane or whatever, 2-methylpropane, you've got two possible regioselectivities. Your halogen radical can abstract a proton, or a hydrogen atom rather, from the tertiary carbon or the primary carbon. And that can lead either to the tertiary alkyl halide or the primary alkyl halide. And if we do this experiment for both chlorine and bromine, both chlorine and bromine have a preference for generating the tertiary radical and therefore the tertiary alkyl halide. For chlorine radical, the preference is 6-4-1, whereas for bromine, the preference is 19,000 to 200-1. Bromine is more selective, and the justification for this is the Cl is less stable than the Cl radical is less stable than the Br radical. You can justify that by looking at bond strengths, homolytic bond cleaving of HCl versus HBr. And as a result, the hydrogen atom abstraction is, because Cl minus is less stable, it is more exothermic, more downhill in energy for Cl radical than for Br radical. And if it's downhill in energy, that means the transition state has to resemble starting materials. That means the transition state is very hydrocarbon-like, which means that the structure of the radical can't affect the rate of reaction very much for chlorine. Okay, any questions about that? Yeah.
Does the same trend hold for fluorine and iodine radicals?
Don't know, actually. That's a good question.
Would fluorine be even less selective?
I think so, but I don't know. It's a good question. Yeah, Isabella.
So is the reaction coordinate diagram you drew there for the first step of that reaction or the second step?
That'd be for the first step. Right. This would be radical and HCl, and then you would go downhill further upon the second step. Yeah. All right. There's many exceptions to this. Your text doesn't tell you any, and I don't know of any offhand, but I think Dr. S knows of tons, and so this is not a favorite principle of his. You will hear it used to justify things, so now you know the origin of it, and just be careful with it. The next one is kind of fun because it's hard to remember the difference between this and the Hammond postulate, because one of the people that enumerated this principle was named Hammett. So if you get confused about Hammett versus Hammond, just mumble a little bit and you'll be fine. Oh yeah, it's the Hammett postulate, the Hammond, Hammond principle. Anyway, nobody will be able to tell. So this relates to situations where two products are possible. And it's really an issue of kinetic versus thermodynamic control. And the idea behind the Curtin-Hammett principle is that if you have a reaction coordinate energy diagram that looks like this, if you have two intermediates that are equilibrating, intermediate 2 leads to product 2, intermediate 1 leads to product 1, and if the barrier between those intermediates is lower than the other two barriers that lead to products, then the relative stability of the intermediates does nothing to tell you, will not predict which products form. And the reason for that,
Could you say that one more time?
okay, so you've got two intermediates or starting materials that are equilibrating between each other. Their barrier from one to the other is low. One is more stable than the other, but the product ratio is only determined by which barrier to products is higher. So in this case, even though intermediate I2 is lower in energy than I1, product 1 is the major product, because the barrier to go from intermediate 1 to product 1, we'll call that delta G double dagger 1, is much less than the barrier to go from intermediate 2 to product 2. Okay? So the Curtin-Hammett principle tells you that the I1 to I2 equilibrium is irrelevant. And I guess to have that make sense, we need to point out that these reactions are The Curtin-Hammett principle is for reactions that proceed to products irreversibly. Okay. This is another statement of the idea of kinetic versus thermodynamic control. When reactions are run under irreversible conditions, the fastest product to form wins, period. It doesn't matter. In this case, the major product is P1. It also happens to be the more stable one, but that's not why it's the major product. It's the major product because it forms faster. All right, so as long as this barrier between I1 and I2 is small relative to this, both of these activation energies, the product ratio is going to be determined entirely by the activation energies and which one is higher. Your text formulates this in terms of an equation. The ratio of product 1 to product 2 will be equal to the equilibrium constant between the two intermediates, and then K2 divided by K1. And so if the barrier between I1 and I2 is small and the difference in stability is relatively small, KEQ is going to be close to 1, and the product ratio is going to be dominated by how fast it is to get over these barriers. All right. Anything more to say about that? Questions? Classic example of the Curtin-Hammett principle is attack of nucleophiles, nucleophilic addition to ketones or aldehydes with stereocenters at the alpha carbon. All right? So, you've got 3 potential rotomers that we can consider for nucleophilic, for our ketone that has a stereocenter at the alpha carbon. And based on what we learned in chapter 2, in general for ketones, you're going to have one group eclipsed with the carbonyl oxygen, and then the other two will be sort of staggered with respect to the other group on the ketone. All right. So you might be tempted in choosing which of these is going to happen fastest to be worried about the relative stability of these rotomers, right? You might be concerned, well, is it better to have the large group eclipsed with that oxygen or to have the large group staggered? Would it be better to have the small thing eclipsed with the oxygen so the other two larger groups can be staggered? And the answer to that question is you're barking up the wrong tree, or that issue is irrelevant, because barriers to rotation around those bonds are on the order of 8 to 15 kilocalories per mole, which is, oh, sorry, that I got that backwards, and so don't write that down. Yuck. So barriers for rotation around sp3, sp2 kind of bonds are in the, based on chapter 2, we would say maybe 0 to 3 kilocalories, 1 to 3 kilocalories per mole, right? In contrast, delta G's for nucleophilic addition to carbonyls tend to range in the 8 to 15 kilocalories per mole. So this is a case where it doesn't matter which is the more stable rotomer. The only thing that matters is which addition happens fastest, okay? So, if we look at these options, which of the 3 options, 1, 2, and 3, do you predict will be faster? And the argument's going to be based on sterics.
I guess the third one.
You're guessing 3. Okay. And they've kind of, I don't know why they did this. They've kind of messed you up because the Berge-Dunitz, which we'll talk about later, and based on where pi stars are, nucleophilic addition from carbonyls tends to happen from that direction. So does that change your mind?
Is M metal there?
No, M is small, medium, and large.
Oh,
Yep.
I thought, yeah. I thought for some reason it was metal ligand.
Yeah, that is confusing too. Small, medium, and large. And yeah, so nucleophile is going to come in along this kind of trajectory. Oh, well, shoot, they're all over the place in terms of which side it's going on. That's kind of great. All right, which one do you like better?
1 and 2.
You look at 1 and 2 as the same. What's different about 1 and 2? Right, 1 has a medium group. It's not directly in the pathway of your nucleophile, but it is on the same side of the molecule. And the other is going to have the large group on the same side of the molecule as the nucleophile. So, which one do you pick? It's probably this one. It's probably this one that happens faster due to sterics. And notice we didn't consider at all which was the most stable rotomer, because the difference in energies between those rotomers is going to be like this on an energy diagram, whereas the transition states are going to be leading to products are going to be way up there. So it only matters which transition state is lowest in energy. Okay. Any questions about that? Yeah, Marior.
So you are looking the studies that is around the nucleophile or around the carbon?
Right, you're looking at faster due to sterics. Basically, the question is, what's going to bump into the nucleophile as it approaches? So I don't know what we mean by small, medium, and large. Let's say proton, methyl group, and then T-butyl group or something like that. The group that's eclipsed with the oxygen matters somewhat, not as much as the group that's in the direct pathway of the nucleophile. But if this methyl group were eclipsed with the carbonyl, you're still going to have a CH bond jutting out on this side, and that's still going to affect things. So in terms of steric hindrance, the approach delineated here in 1 is better because it gets to approach it gets to approach the side of the molecule that has the smallest group on it, and then the next smallest group at the place that eclipsed with the carbonyl, and the biggest group is far away on the other side. In contrast, this one, if we're talking about T-butyl group versus methyl group, the nucleophile approaches, and even though that T-butyl group is eclipsed with the oxygen, it's still going to be big enough to sort of get in the way as the nucleophile approaches. All right. So the Curtin-Hammett principle is an example of kinetic versus thermodynamic control. If a reaction is irreversible, the only thing that matters is which product forms faster. Okay? So kinetic control really just refers to if a reaction is irreversible, run under irreversible conditions, then fastest to form is the major product. Under thermodynamic control, these are run under equilibrating conditions where starting material and product interconvert, many times, and the only thing that matters then is the most stable product. How do you run reactions under kinetic control? You use really reactive reagents and you do it at low temperature. And really reactive reagents will have a reaction that's very exothermic. You run it at sufficiently low temperature and you basically prevent any of the products from going back over the hill to starting materials. And then if your starting material can go into two different products, maybe product 1 and product 2, even though product 2 is more stable than product 1, forming product 1 is faster, and once you get there, you are stuck. Yeah.
There's no way to dig a tunnel of any kind.
That's right. There's no, try as you might, right? There's no,
If you did that, you'd be catalyzing the reaction.
yeah, I don't know. Yeah, and what catalysts do is they either change the mechanism or lower the energy barriers to allow reactions to occur that wouldn't otherwise occur. All right, an example of thermodynamic control, you might think about, and this is a terrible reaction to run, E1 elimination, where which is usually of let's say alcohols under acidic conditions. Dehydration of alcohols under acidic conditions. Get to the carbocation and then shoot. This is a dumb example because there's no options. So I don't have a good example of thermodynamic control off the top of my head. A classic example of that is, and I could think of one, it's just not coming to me, E1 dehydration of alcohols to give alkenes, and you get the most stable alkene as the major product. And the reason for that is that the reaction's reversible, you can go backwards, and therefore the major product is determined only by the equilibrium constant. Okay, anything else we want to say about that? All right, so let's talk about kinetics and how to control a little bit about kinetics, a little bit about how to control reactions. I want to start with an important concept that's derived from kinetics, but is important in...
Josh, just a quick question.
Yeah.
So if the most thermodynamically stable product is not the one that's formed, do we assume that it's kinetically controlled?
If you get a product that isn't the most stable one, do you assume it's under kinetic
Like, I mean,
control?
what is it? It's been so long. Hydration oxidation, right? You get the less substituted alkene.
Yeah, that's not an issue of...
It's just transition state, right?
hydration oxidation gives you the alcohol on the less substituted carbon,
Right.
but that's because of the characteristics of the reagent. It still follows the buildup of partial positive charge in that reaction is still on the more substituted carbon, though the product is anti-Markovnikov regioselectivity.
Okay.
Yeah, but not for a different reason. All right. No, but I'm not sure. I don't know that you can assume if the thermodynamic product isn't the major one that you're under kinetic control. It sounds good to me, but I'm not sure it's always true. It's worth thinking about, but I'm not sure. All right, there's a concept in chemical biology and physical organic chemistry called effective molarity. And this is used to explain why intramolecular reactions are faster than intermolecular reactions, and to put a number on it, which is kind of cool. So let's consider the SN2 reaction of some bifunctional amino iodide, and it can go through reaction 1 with K intra, oh, nope, I got it backwards. I want to follow what your text does. K intermolecular, where a nucleophile on one of our molecules reacts with an alkyl halide on another molecule. You get the intermolecular reaction, and you end up with this bis iodide. Oh no, sorry. You displace the iodide, you'd end up with this molecule, which itself is bifunctional, and it could continue on to react to give you a polyamine polymer. Okay, alternatively, you could have the intramolecular SN2 reaction with the following rate constant, and that would generate the cyclic product. Okay, and that we would call that reaction 2. And if we looked at the rate of formation of, let's see, the rate of reaction 1 is going to depend on the intermolecular rate constant times, and we'll call this starting material I, because that's what your book does. Because it's an SN2 reaction, that's got to be second order, right? The rate law's got to involve 2 molecules of that starting material. In contrast, we could write the rate law for reaction 2. That's going to equal the rate constant for the intramolecular reaction, and now you only have 1 molecule of your starting material in the rate law because it's an intramolecular reaction. And so you could ask, what is the difference in rates? What's the ratio of the rate for reaction 1 divided by the rate for reaction 2? Well, that's easy. K intermolecular times I to squared over K intramolecular times the concentration of I. And you end up with the following expression that tells you that it's going to depend on the intrinsic rates of the inter versus intramolecular reactions, but then also on the concentration of your starting material, which makes sense. This is why when you want to do a cyclization and you don't want to get polymers, you run it under dilute conditions, because that slows down the intermolecular reaction. But your text goes further and says that you can think about the ratio of rates between these reactions as the concentration of your starting material divided by the effective molarity of the 2 groups in your starting material in the same molecule. And that effective molarity equals the rate constant for the intramolecular process divided by the rate constant for the intermolecular process. Notice that the rate constant for the intermolecular process is going to have units of per molar squared, whereas the rate constant per molar squared per second, I guess, whereas the rate constant for the intramolecular reaction is just going to have units of per molar and then per second. And so overall, effective molarity has units of molar. So if you calculate the rates of an intra versus intermolecular reaction, you can get the effective molarity of those 2 groups with respect to each other. And that's just kind of an interesting way of thinking about cyclization reactions and how they can happen. Because they're constrained in the same molecule, it's like you've made the concentration higher artificially. In an SN2 reaction, you got to bring two things together. Well, you've already done some of that when the two things are in the same molecule. So you will hear people talk about, oh, this increases the effective molarity of this group and causes a reaction to happen. And this is one of the things that catalysts can do. So Dr. Michaelis has a project, right, Adam, in your lab. You're making peptide catalysts, and how do they? What's the idea? How do they work?
You put both catalysts on the peptide scaffold, and so I guess increases the relative concentration around that peptide.
Right. You have a catalyst 1 and catalyst 2. And the idea is that this is going to bind A and this is going to bind B. It's going to bring them close together. And ideally, now the process is unimolecular. And so that will presumably accelerate the rate. And a way to think about that is, oh, you've increased the effective molarity of those two groups. All right. Anything else you want to say about that? Better come up with something, because next is math. Maths. Okay. So I want to show you a little bit about rate laws to get an idea of the kinds of experiments you might do to assess kinetics of a reaction. So we're going to talk about a first order reaction, and this is easy. This is A starting material converts into product P. The rate of the reaction you can represent as the change in concentration of P as a function of time. If you monitor P, if you have a spectroscopic way to monitor P, you can measure the rate that way. Alternatively, you can monitor the disappearance of A. So it makes sense that as P appears, A disappears, and that's the reason for the change in sign. And we'll write that rate law for a first order reaction. There's a constant and then multiplied by the concentration of A. We can integrate this rate law to get an equation that tells you how the concentration of A is going to vary with time. So let's just take the expression dA dt equals minus Ka. When you do integration, you want to get the two d's on opposite sides of the equation, and you want to get the variable over here that corresponds to the variable in this derivative on the same side of the equation. So to do that, we just divide both sides by the concentration of A and divide both sides by dt, and that gives us this equation. You okay so far? Ish?
I'm just smiling because it was a Chem 112 for response question.
Okay. Free response question, Chem 112. Okay, then Kim, tell me what to do next.
Integrate.
Integrate from where?
From 0 to
0 to t over here, and then starting concentration of A to whatever the final concentration of A is. Okay? So over here we end up with minus kT. Over here we end up with the natural log of A minus the natural log of starting concentration of A, which you can rearrange and come up with, and often that's good enough, but if you wanted to just be dealing in concentration of A instead of logarithm units of A, you've got that. Okay? That's a first order integrated rate equation, and that's the easiest one. That's the kind of one that you maybe ought to be able to do in your sleep, not because I'm going to ask you to do it in your sleep, because that's kind of boring, but it's good to know where that comes from. For first order reactions, they will often talk about T1/2, meaning the half-life. And this is basically how much time has to pass before A equals 1/2 of A naught. All right, so starting with this equation, let's let the ratio of A over A naught be 1/2. So natural log of 1/2 equals minus KT. Multiply both sides by -1. Natural log of 2 equals KT. Natural log divided by rate constant gives you your half-life. That's an interesting rule of thumb to remember. You want to calculate the half-life. All you need is the rate constant and the natural log of 2. But that's how people talk about these kinds of things. All right. Your text gives an example in one of the interesting boxes, but we are done, so we'll pause there for today, and we'll pick up with more maths next time. I owe you an exam, which I will give to you later today. So stay tuned for an email, and then we'll schedule times to come talk to me on Thursday.